Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, IoT, robotics and other fun tech. Today I want to celebrate the release of version 11 of the FreeRTOS kernel. I use FreeRTOS a lot in my projects. It gives me tasking and task communication primitives for the Raspberry Pi Pico and Pico W. The new version is something I've been long waiting for, as it merges symmetric multiprocessing version with the main codebase. So at last I can easily upgrade my projects to run on both of the cores of the Raspberry Pi Pico. I'm going to demonstrate this today with a simple example. I'll measure the performance of the Pico in terms of the number of calculations of the mathematical value of pi it can perform in a minute. I'll baseline FreeRTOS kernel against some hand-coded Pico SDK examples. The results are good, but not quite what I expected. Stay tuned to see why. Before we take a look, please do like the video and subscribe. I do appreciate it. The concept I want to explore in this video is about measuring the amount of work we can get a Pico to do. It's speed, if you like, but it's in speed in terms of workloads we can explore. And I want to look at two different approaches to this. Bare bones, that is, just using the Pico SDK in C or C++, and to do that using both a single core or to use two cores. And obviously if we use two cores, we ought to be able to get twice as much work done. Though it won't be quite that, but we'll be close. And then to explore how does that change in terms of workload if we are doing this through FreeRTOS. There's a bit of a myth that running FreeRTOS as a framework means that there's a lot of additional work going on in the background around scheduling and management of the environment. And to an extent that's true, but let's have a look and see how much does that actually affect the amount of work we can get done. Again, let's look at that in a single core model, and we can look at it in a dual core model. This time dual core should be a lot easier for us because it'd be managed by FreeRTOS rather than us having to do the work ourselves. So we need some work for our Pico to do, and the work I've decided to do, ironically, is to calculate the value of pi. That seems sensible for a Raspberry Pi product to do, to calculate pi, and we can calculate pi to 1,000 decimal places, which is quite a lot of data. That's going to take the Pico a little bit of time to calculate. In fact, it can only calculate about 3 to 4 of those a second from the approach I want to do. There are several approaches to doing this, and the algorithm I've chosen to do is called Spigot. And I'm not even going to go into the maths of this or how that works because I'm going to use someone else's library that's already done this. And so a guy called Elias, and Elias has already written this in C++ in a nice usable library where we can tell it how many decimal places we want to calculate and set the C++ code off to go and do it. So let's use his library to do this. As always, I'm going to share all of my code for these 4 examples I'm going to show, and it's all on GitHub for you to go share and look at. I've placed a link in the description. I could not produce these videos without sponsors. Today's video is sponsored by Cancun, my favourite UK retailer for components. Cancun has kindly offered a discount of 20% on the first order for you. Just quote Dr. John EA at checkout to get a 20% discount. So go check out Cancun today. Right, let's look at a bare metal version, so just using the Pico SDK with a single core running sequentially to calculate the value of pi to 1,000 decimal places. So in Visual Studio, I've got up the repo here. Now the first thing I just mentioned is that we have a shared lib folder here, which has got the Pi SPI got library within it, and it's also got FreeRTOS kernel in it. If I go into this great library that we're using, that you'll notice that it's actually using quite advanced templating. techniques in C++, which is really cool and really great, but also slightly beyond what I've been using previously in my Pico projects. So I've had to do some slight changes to the make environment. So one core is the first example. So this is just linearly running pi calculations in a single core. And here we've got where we're setting the version of C++ that we're going to use for the compilation. And as you see, I've rolled that forward to CXX standard 26, which is the latest C++ standard. That's quite a way forward from 17, which is what I was traditionally using for my Pico projects. The good news is it's caused no problems. I was thinking it might interact with some of the SDK, but it's been absolutely problem free. Nothing else in the make system for this example is any different to what you'll normally see. As usual, I'm including my make file for building my library, and I tend to also set a variable of where the location is. It lets me rely on either my normal standard of a library is within the project, or in examples like this where I'm actually using one library that I've downloaded once and I'm just sharing it across 4 different projects. So the program itself is actually just one class, which is our counter here, and one main. The reason I've created this counter is actually I want to have the same counting process and output across all of the projects. So I've just written one class that's going to do it. So I can start the counter, I can increment to say that we've actually done another power calculation successfully, and then when the 1 minute I'm going to run this for completes, it can run a report. Actually, both the versions of increment here are taking some parameters. So firstly, I want to calculate and allow myself to give several IDs to the calculators of pi. So if we're running across 2 cores, I might have core 0 being calculated as ID 0, core 1 calculated as ID 1, so I can give myself a little bit of a stats and see what's going on under the hood. When we get to FreeRTOS, we actually want 2 dimensions of stats. I want to know not only which task is running stuff, but also which core ran it as well. And so there's a little bit of that going on under the hood. So on the manual one here, because Inc actually works out what core you're on automatically, Incore is actually allowing me just to give it the ID and give it the core number, so that I can calculate. For what we're running in this example, this first example, actually everything's just going to be 0 because it's linear. We've only got one value and one worker and one core running. So let's have a look at main. So let's have a look at the main function itself. This is really very simple. All we're doing is starting up as normal. I'm going to set up an alarm callback. So in exactly 1 minute, I want it to call back and call the function alarm callback. That's it, and that's what I'm going to use to stop stuff. Then I'm going to start our counter so that we can start counting up the number of calculations we can do, and then we're going to go through a loop and we're going to keep doing this function do work. And every time we've done work, that's a pi to 1,000 decimal places that we've calculated, and we can increment our counter. That will keep going forever, which is fine, because actually the counter will automatically stop as soon as that timer triggers. We've got the timer code up here. As soon as the timer triggers, it actually runs report, and report stops all further counting. So what does do work look like? Well, do work is setting up this pi calculator there. It's giving it some vectors to work with, and actually I would say, so it's worth setting up with 1,000 decimal places it wants, and it's giving it a space of 9 units or 9 places in order to speed up the calculation. So it's going to use slightly more memory, but anyway, that's just one of the parameters into the library. Not something to particularly worry about. So we can then create our input container and our output containers, and the library will tell us how big they need to be based on those two stats there. And then we've got our nice calculator, which we're instantiating there, and we can tell it to run off and calculate, and that's it. And that will give us the value of pi to 1,000 decimal places. So running with one core, we're able to calculate 184 values of pi within 1 minute, which isn't bad really. That's just over 3 a second. So let's do this running again in bare metal, but this time with a dual cores. So using both cores, so we ought to get almost twice as many calculations. Now we've got a little bit of a complexity here because I'm only going to have core 0 add to our counter. So when core 1 finishes, it needs to somehow tell core 0 that it has calculated a value of pi. To do that, I'm going to use the inbuilt FIFOs. There are two FIFOs associated with the cores, that's in, first first out queues, and we can use those to send messages from core 0 to core 1 or core 1 to core 0, as in this case. So all I'm going to do in this example is every time I complete, I'm just going to plop a value into that FIFO, almost like plopping a ball bearing into our queue, to say, actually, I've done a calculation, it's complete. Core 0 can then keep the totals. So 2 core is the example that's going to run bare bones with the 2 cores. And we've just talked about FIFO, so we know we're going to use that FIFO to move between the 2 units. So the only difference in code here is in main. And again, we've got that callback function, which is just going to report. We've got the same do work function, which is doing exactly the same calculation of pi. And then we've got our main function. I'll come back to core 1 main in a second. So the main first thing we need to do is just reset core 1 to make sure the second core, remember cores on the Pico are called core 0 and core 1. So the second core, we're going to reset it, core 1, and we're going to drain the FIFO. So I'm going to make sure there's nothing in that FIFO coming from core 1 to core 0. We're going to set up our alarm callback once again, as usual. To call back after 60 seconds. And we're going to once again start off the instance, start the counter. Then I'm going to launch core 1, and I'm going to give it basically a function to go and run, and that's going to go and run on core 1. We'll talk about what's in that function in a second, but let's have a look at our loop. Our loop's got a little bit more complicated. It's at the end of it, we are still doing work. So core 1 is still calculating the values of pi, but the first thing the loop is going to do is it's just going to check to see, is there anything in this FIFO coming from core 1? So has core 1 completed any work and calculated any values of pi? Every time we find a value in there, and I'm basically ignoring the value, but I'm just saying if one value turns up in that there, we pop it off, so we cleared it down, and we increment a new instance into our counter. And I'm using the in-core function here so that I can force to tell it that actually I want it ID'd as 1 and I want it to be categorized as running on core 1. So what's in our core 1 main function? Well, that looks very similar to our previous stuff. All we're actually doing is saying, right, run dwork multiple times. If dwork succeeds, then push the value 1 into our FIFO. So every time we successfully calculate a value of pi, we push a message over to core 0 to tell it we've actually done that. So in dual core bare metal mode, we've actually are managing nearly twice as many. We manage 360 calculations of pi within 60 seconds. More of them are being done on core 1 than core 0 because core 0 is busily checking and working on that queue and making sure that it's doing all the count calculations. I must admit that it's causing more load on core 0 than I was expecting in this example, but still pretty pleased with the example. The answer 366 per second. That's pretty good. That is almost double what we were getting on the last example. So I'm going to tweak our workload to be able to run under FreeRTOS in a single core model. And let's see what that gives us as calculations and what the overhead of FreeRTOS turn out to be for our workload. So one RTOS is our single core FreeRTOS example for doing these calculations. And as always with FreeRTOS, I've got port code here to port that over to my environment running on my Pico. This is going to run against version 11 of the FreeRTOS kernel, and that means there are a couple of changes from things I've done in most of my FreeRTOS stuff in the back previously. I can no longer use some of the approaches to build FreeRTOS that I used to use because they've actually been deprecated. So instead, for the configuration, you'll see here that there's actually a CMake file for the actual port code, and I'm putting that in a FreeRTOS configuration. So that gives me all the memory management, log levels, any other idle memory, and all of the other bits of configuration we need to get FreeRTOS up and running. Most of that's code I just copy from project to be honest. So let's have a look at the main code of this example. There are a couple of other classes that have appeared now. Firstly, my agent. That's basically just a way for me to go from the world of tasks and as C functions in FreeRTOS to actually running that as an active object. And that's my approach that I tend to like to run FreeRTOS. Our code for calculating pi has then migrated out of main into worker. So worker actually is going to be an agent, so it's going to be a task in itself. It's going to run itself in that run method, and it's got the do work function copied over to it. Let's have a look at main and normal stuff. So in main, we've absolutely got our main alarm callback function still, so that I'm still using the same strategy of setting up a callback alarm to call back after 60 seconds and stop the counters. My main function this time is kicking off a boot thread in FreeRTOS and starting up the scheduler, and that's all it's doing. Nice and simple, common for just about every FreeRTOS application I ever write. And that main task, which is this function here, is going to create two workers. So although I'm running on a single core, I'm actually going to make it a little bit more interesting and give myself two workers, both of which are calculating the value of pi and both of which are updating our counter. Again, we've got a callback after 60 seconds, and so this is now just going to basically start the counters and start the two worker threads running, and that's it, and off it goes, and when it's done we will get the answer. So let's have a look at what the stats come back from this one. The stats on this one are really quite interesting. We absolutely see a comparable performance to what it was on bare metal single core. To my great surprise, the performance is actually slightly better, and I'm managing an additional 4 calculations within a minute, so we're 188. They're split evenly between the two tasks, which is really nice and maybe a version 11 feature, because I was actually expecting one of the tasks to actually dominate. But anyway, why is the performance better on this than it was on bare metal? Why have we got that additional 4 calculations? I'm not quite sure. I think I need to go and actually have a look at this in a bit more detail. What do you think? Let me know in your comments what you think might actually be going on. So let's try this dual core. And now with FreeRTOS kernel version 11, I can do that without having to actually pull down a different version, create a separate library, or all of those nasty things I had to do in the past, and in fact change the build system. I can in fact just change the configuration file to say that I want to run on dual core, and everything else will just magically happen. So 2RTOS is running on 2 cores with FreeRTOS. Now the code here is actually going to be incredibly similar to what we've seen previously. So let's have a look at main. So we've still got our long callback. We've still got our main task calling up and starting FreeRTOS and starting a boot thread. And in that boot thread, we're creating some workers and starting our counters and then starting those workers. This time I've gone a little bit over the top and created 4 workers. So we've got 4 workers calculating the value of pi. But apart from that, this is, from this main file is concerned, the code's actually identical to what we had in 1 core. So what's changing it to be running across dual cores and dual ports? I think all of the configuration changes I've made to make this run multi-core are around here in FreeRTOS config. And it is simply actually this section down here where we're actually defining that we want to run in FreeRTOS Kernel SMP, and we're configuring it to have 2 cores to and turn on core affinity and passive services. It's this bit of code down here, that's the only thing that now switches us from running 0 on just core 0 to running across core 0 and core 1. Now, isn't that fabulous? All of that work with FIFOs, all of that worrying about setting up and then clearing a core, initializing it, thinking about all of that goes away. Actually, all of that's now done for us by FreeRTOS, and by changing a couple of definitions in the configuration for FreeRTOS, suddenly we're running across 2 cores. Let's have a look at the stats. So running multi-core, I am expecting a little bit of degradation. There is quite a lot of overhead around running the scheduler across both cores. So it isn't going to be as performant as our handcrafted bare metal version for 2 cores, but it's not bad. 336 calculations within the minute, and that's split nicely and evenly, 84 in each of the tasks. So it did really well, 5.6 per second against 6 calculations per second, which was our maximum on our handcrafted. The point of running bare metal just with the Pico SDK is to give us a baseline, and to use that baseline then to compare the similar values be for FreeRTOS running in single core or dual core. And actually the performance is really good on FreeRTOS. I'm really impressed. This is especially when how easy this is to get running multi-core, and then to have all of that communication capability that FreeRTOS gives us to communicate between those tasks. So really cool stuff. If you'd like to learn more about FreeRTOS kernel, then I've got a course on this on the Udemy platform that talks about this on the Pico, and how to get tasks running, how to then put semaphores or messages to communicate between those tasks. I'll put a link in the description, and for the next few days only there'd be a discount code too. The merge of the SMP code into the main release of FreeRTOS is something we've all been waiting for. My congratulations and thanks to the team working on FreeRTOS kernel for getting this out. It's a really fabulous library to have available for the Raspberry Pi Pico. Thank you very much for watching this video. Please like the video as it helps others find it, and it gives me encouragement to work on the next one. And please subscribe and hit that notification button so you don't miss it. Goodbye for now.